let P be the pattern and alpha gamma beta be the range of the receipt query. So we will locate, we search for pattern P in the suffix tree. Let B be the node at which the search terminates, and L be the path on which this node is present. So we will query the corresponding data structure with the vertical query segment D into alpha gamma beta, where D is the depth of node B. So this will be like this one. So the pairs associated with the horizontal segments will form the output set. For the top tier queries, the first three steps will remain as it is. Only in the last step we query the data structure with the array, vertical array emanating from the point D minus infinity, and we report the first k segment intersected by this ray. So pictorially here we can see ray intersects all 5 segments, but we need to report only the first 3 segments. So in each case we are spending order of m plus log n plus output size time to answer a query. This is optimal if m is larger than the log n. However, this is not true for the other case when m is just smaller than the log n. So for that case, we augment the suffix tree with some information. So for each node in the suffix tree with length not more than log n, we will store the list of consecutive occurrences sorted by their distance. So by using this information, we are able to improve the query time bound. For top tier, we get the optimal, and for the water-based query, we have additional log alpha vector. So we have there are few questions which are related to this problem. All the solutions which are existing, including this one, have uses this bound order of n log n. So it is possible to lower down the bound linear size. And the other is to, instead of considering the whole string, if we concentrate on the particular on a substring, what could be the bounds for it? Okay, any question?
There is a lot of time for questions. Any question? So this is a data structure problem, right?
Yeah.
So there are 2 objectives, that is space and query time. So is there any lower bound? No? I didn't see you presenting any.
So we are not aware of lower bounds. I think we can improve the space bound. The query time is optimal, but what we can do is the space we can move on to the linear space, but we are not aware of the linear space.
Okay. Thanks. Yeah.
Thanks for the talk. So you had a part on the top K query. So what was the ranking criteria? Can you
So when we creating the horizontal segments, so the y coordinate area, this is j minus. This represents the distance of the consecutive occurrence. That is our immediate concern with. So problem is that we need to report the k consecutive occurrences with minimal distance. Okay, so j minus y is the distance of it. So y coordinate of the horizontal segment represents the.
Okay, thank you.
More questions? In that case, let's thank the speaker again. The next talk is scheduled at 11:40, so we'll start it. Still, should be.
Yeah, let's continue this.
Okay.
Or you want to wait? What is the?
In case somebody planned to attend the second talk, show them a different point.
Okay, then. Huh?
Hello. Hello. মাথা পিছন দিকে এটা ঠিক আছে 11:40 স্টার্ট হোক এটা মানে বন্ধ করার পর
The next speaker is Gautam Abde, and the title of his talk is Parameterized Aspects of Distinct Chemical Rank Aggregation.
Yes. So, myself, Kaustubh De. This is a joint work with Harshil Mittal, Professor Polasde, and Professor Nildhara Misra. So, I am presenting our joint work named Parameterized Aspects of Distinct Chemical Rank Aggregation. Yes, yes. Okay, okay. Yes, yes. Okay. So, I will start the presentation with a brief description of fixed parameter tractability. So, a problem is said to be fixed parameter tractable if it admits with respect to some parameter k, integral parameter k, if additionally it admits an algorithm with runtime, say a function of k times n to the power of 1. So we say that the problem depends polynomially on the input size n, but it may or may not depend exponentially on the integral parameter k. So let's say we have a set of candidates C, and by votes I mean that every vote is a linear order over the set of candidates. So let's say C is a set of candidates containing A, B, C, D candidates, and each vote pi in big pi is a linear order over the set of candidates. So let's say pi 1 is a linear order of the candidate set, pi 2 is another, and pi 3 is another. These are the example set of votes. And the distance metric between any two linear order is considered as the Kendall-Tau distance. So Kendall-Tau distance says that between any two linear order, the number of pairs of candidates on which the votes disagree, the number of pairs of candidates are counted that counts to that Kendall-Tau distance. So here is an example. Let's say the same pair of votes are repeated here. Let's say pi 1 is a linear order and pi 2 is another linear order. In this instance, only the pair of candidate BD on which the two candidates, the two linear orders disagree. And there are other pairs of candidates on which the linear orders disagree, like BC and CB here, and BA and AB here. So all the pairs of candidates which are marked red, like they count to this Kendall-Tau distance. Yes. Yes. Yes, it is also shown here. Like the pairs of candidates are marked red. Yes, yes. Yes, yes, number of pairs on which the linear orders disagree. Yes. Okay, okay, okay. So let's say we have a, set of votes, and the votes are nothing but the linear orders over a set of candidate, and we have to compute a K-mini consensus, that is a ranking which has minimum K-mini score. So what do I mean by minimum K-mini score? So from L, from all the linear orders, this linear order which we want to compute has a distance Kendall tau distance, like kt is L pi. So I have already defined what is Kendall tau distance, and we take the summation over all the votes, the distance sum over the Kendall tau distance from all the votes of that ranking L, and this is the K-mini score. So L is the K-mini consensus if this K-mini score is minimum, and see that between any two ranking, the number of pairs of candidates on which they disagree can be at most m choose 2. So since there are n votes, so the K-mini score can be at most n times m choose 2. So the authors Dwork et al. Have already showed that the problem is NP complete even when there are only four. The input instance is restricted to only 4 votes. So here are some preliminaries. So for every candidate in a ranking, the position of C in that ranking pi is defined as the number of candidates which appear before C in that ranking. And the range of a candidate C is defined as, let's say pi and pi j are any two vote in the input profile of votes, and we want to take the difference of position of C in those two rankings, and like we try out all possible pairs of votes, and we take maximum over the differences of positions. And there is a plus one in the sense that suppose every vote in the profile has ranked the particular candidate C the same, so we want to say that the range of C is at least 1. That's why we are adding 1 to this range. Next, rho is the unanimity order of the voting profile big pi. So what do I mean by unanimity order is that, let's say a pair of candidates is AB, and all the voters agree that A should be preferred over B in their ranking. So then the ordered pair AB will be included to rho. So in this way, rho contains a set of ordered pairs AB of candidates on which all the voters agree that A is preferred over B. K of pi is the set of optimal K-mini rankings with respect to pi, like which has the minimum K-mini score. And K pi k is the set of K-mini rankings where we say that the K-mini score is at most some integer k. And n pi xy is the number of linear orders in the voting profile pi, where x is preferred over y. So here are some problem definitions. So distinct K-mini rank aggregation. In this problem, the input is like the set of votes pi, set of candidates C, and like parameter k and r. K and r are the additional parameters. So we want to compute minimum r and mod k pi distinct rankings, such that every ranking respects the unanimity order of pi, and K-mini score of each ranking is at most k. In case of distinct opt-k array, the only difference is that we compute minimum L and mod k pi number of distinct rankings, where the K-mini score of each ranking is the optimal, like minimal K-mini score. And in case of distinct approximate k array, the K-mini score is lambda times the k opt pi. K opt pi is the optimal K-mini score of the voting profile pi. And here also the each ranking respects the unanimity order rho. So there exists a Turing reduction from distinct opt k array to distinct k array. Like if there exists an algorithm for distinct k array running in time O of f mn, then there exists an algorithm for distinct opt k array running in time O of fn log mn. So recall that optimal K-mini score can belong in the range starting from 0 up to nm2. 0 because if all the votes are same, and then the optimal K-mini ranking will be one of the rankings. So the sum of Kendall tau distance from all the ports is 0, and it can be at most n times m choose 2. So we perform a binary search in the range from 0 to n times m choose 2, and to find the smallest k, such that the like algorithm for distinct k array outputs at least one ranking. So if there exists an like this claim holds, like we have an algorithm for distinct k array, like we have an algorithm for distinct of k array also. So here are the summary of results. Uh, Here are some like a PT parameterized algorithms. So K is the K-mini score K, M is the number of candidate, D is the average Kendall tau distance, R max is the maximum range of a candidate in the profile, and W is the if like we create a graph of the candidate, and there is a like order row, and we create 0 as the co-comparability graph of that voting profile. So W is the pathway of the path decomposition of 0, and R is the number of rankings we want to output. So there exists an algorithm for distinct k array parameterized by the K-mini score K. This is a bounded search tree based algorithm. So this is the problem instance we want to reduce at each level of the subtree. And after each recursive call, we claim that the K-mini score K reduces strictly by at least one. Since row is the unanimity order, uh, let's say a pair of candidate AB on which all the voters do not agree. So neither AB belongs to row nor does BA. So n pi BA, recall that n pi BA is the number of linear orders uh, on which the number of linear orders in pi where all the voters agree that B should be preferred over A. So number of linear orders in pi where B is preferred over A. So K strictly reduces by at least one, since row is the unanimity order and AB does not belong to row. Likewise, in this recursive call also, we include this pair BA to row, and we take transitive closure. And we solve these instances recursively. Since the K-mini score reduces at least by 1, so the depth of the tree is bounded above by K, and the number of leaves is at most 2 to the power K. And we claim that our optimal our K-mini rankings, where the K-mini score is at most K, uh, belongs to one of the leaves. Like it definitely belongs to in the leaves. So the runtime also of the algorithm is bounded above by 2 to the power K. So we have another algorithm for distinct approximate K array. Parameter is by K and lambda. Lambda is an additional parameter. So if we replace K with lambda key in our previous algorithm, so we come up with the following: that there exists an algorithm for distinct approximate K array running in time big O star 2 to the power lambda K, where the parameters are both lambda and K. So we have another FPT algorithm parameterized by number of candidates. So in this algorithm, we are doing by dynamic programming approach. So each entry in the table is indexed by a non-empty subset of the candidate, and at each entry we are storing minimum R modest factorial number of distinct rankings with least K-mini score. So the update procedure is like this. Let's say this by this dotted rectangular region, these are the rankings stored in TS minus C1. So I have enumerated the candidates of S. S is a non-empty subset of C by, let's say, C1 to C mod S. So let's say this dotted rectangular region contains the rankings which are stored in TS minus C1. So first I place C1 above all the rankings and I consider their K-mini scores. Likewise, this set of rankings are stored in TS minus C mod S, and we place C mod S above all the rankings, and we consider the K-mini score of that rankings, and we find out that like we have to store minimum R mod S factorial rankings in any particular table entry. So since there are like at most 2 to the power mod C or 2 to the power m subsets of the candidate set C, and updating each table entry takes some polynomial r to the power o of 1. So that depends on how fast we can access the uh, like access the ranking stored in a table entry. So the runtime is bounded above by, like the dominant cost is 2 to the power m times r to the power o of 1. So let's see why this is correct. So let's say S is a set of candidates, S contains a set of candidates, and there is a ranking, which is like one of the rankings stored in TS. So then, since it is one of the rankings stored in TS, so this must be a K-mini ranking of the votes restricted to S. But then C2 to CL is also a K-mini ranking, which are restricted to S minus C1. If not, then there must exist another ranking C2 prime to CL prime, of which the K-mini score must be strictly less than the K-mini score of C2 to CL. So consequently, the K-mini score of C1 uh, greater than C2 prime to CL prime is strictly less than the K-mini score of the earlier ranking C1 to CL, which is a contradiction to our assumption that it was a K-mini ranking. So this concludes the proof. So there is another algorithm for distinct approximate KRA parameterized by the same number of candidates parameter. So let's take C pi lambda be an instance of distinct approximate KRA. We run the previous algorithm on the instances like C pi 01, C pi 11. Only the lambda part we are changing of distinct KRA. We stop once we encounter a yes instance, say C pi k star 1, where k star is the optimal K-mini score. So now we run the same algorithm on the instance C pi lambda times k star r, because we want to output the K-mini score, K-mini rankings, whose K-mini score is at most lambda times k star. Since recall that the optimal K-mini score is upper bounded by mod pi is n times m choose 2, and a single run of the algorithm takes 2 to the power m times r to the power o of 1. So the overall running time cost is still b goes to 2 to the power m times r to the power o of 1. And since r is upper bounded by m factorial, so this distinct approximate KR is also a PT parameterized by m. So we have an algorithm for distinct of KRA parameterized by the average Kendall tau distance d. So first we have to understand what is an average position. So average position is taken as the, like every candidate has a position in a ranking pi. So we take the sum over all the positions of a candidate in all the votes, divide by n. This is the average position. And the average Kendall tau distance is, we take the we try out all the possible ordered pairs of votes, and we take the Kendall tau distance, we calculate the Kendall tau distance between such ordered pairs, and we take over all possibilities of such ordered pairs of votes. And we, since there are n times n minus 1 ordered pairs of votes in voting profile pi, so the in this way we calculate the average Kendall tau distance. So Berzler et al. Has showed that, they have showed that like every candidate has a position in a K-mini ranking pi. This is fixed. Average position of a candidate is also fixed, but this position of C in a K-mini ranking pi will always be in the specified range. Like it cannot lie, like a candidate C, the position of a particular candidate C cannot be outside of this range. So average position is fixed. The right side there are d minus 1 gap, and the left side d minus 1, and the average position itself. So every candidate has 2d minus 1 positions where the pose C of like pose pi of C belongs. So pi is a set of candidate where, like I have told before, just before that, this in this algorithm, in this problem, every candidate has a set of fixed positions in a optimal ranking. So pi is a set of candidates for which these 2d minus 1 positions have common, like these positions have I as common position. set of all candidates for which I is their common position in their 2D minus 1 range. So it is also the cardinality of PI is upper bounded by 4D. And partial K-mean score is a score induced by a candidate C and a candidate subset A, where we say that this score is a K-mean score, score when all the candidates of A appears after C in an optimal ranking, because this dA pi CC prime is 0 if C is preferred over C prime in a pi, and it is 1 otherwise. So if C prime belongs to A, C prime is preferred over C in a ranking pi, and in an optimal K-mean ranking we say that all of A appears after C. So then only this it contributes to the K-mean score. So this is a visual representation of PI. So let's say PI contains the set of candidates C1, C3, and C8. So let's say C1 has the set of positions around its average position. C3 also has a set of positions, and C8 also has set of positions around its average position. All of them has I I as common. So all of the candidates will be considered in the subset PI. So this dynamic programming algorithm is based on the fact that it constructs the K-mean consensus from left to right. So when we are at position I, we know the ranking of the set of candidates that appear before I, but the latter part is not fixed, but it will get fixed once the algorithm proceeds. So at every table entry, we store minimum R mod pi number of partial K-mean scores of optimal K-mean rankings restricted to L union C, such that C takes position I, all of L have positions 0 to I minus 1, and all other candidates have position I plus 1 to M minus 1. So for all positions of I starting from 0 to M minus 1, and for all C belongs to Pi, and for all Pi prime is a subset of Pi minus C, there exists a table entry. So suppose Pi contains a set of candidate, and out of this, one candidate is fixed, like algorithm fixes for a particular position I. So the remaining candidates can be either left or right of C. So we try all possible two partitioning of the subset of candidates Pi prime, that is a subset of Pi minus C. So L is the set of candidates on which we take the minimum partial K-mean score, where all possible orderings over L we try out, and we know that C will take the position I, and we calculate the partial K-mean score of all the other candidates like C minus L union C. Like those candidates will appear after C in an optimal ranking. So this is the rough description of the algorithm. So why this is correct? Because after fixing a candidate for a particular position, we manipulate L, and based on the Pi prime, like which candidate of Pi minus C goes to the left side or which goes to the right side. So we try out all the possibilities for L, and consequently C minus L union C will be adjusted. So since we try all the possible subsets of Pi minus C, and Pi, the cardinality of Pi is upper bounded by 4D. So the runtime cost is upper bounded by B go star 16 to the power D. And if at all minimum, like R is the parameter of the algorithm, additional parameter. If at all R number of K-mean rankings exist, this algorithm successfully outputs like the ES instance. There exists an algorithm for distinct approximate KRA parameterized by both D and lambda. So it is also like the previous algorithm. Here the position of a candidate C in a K-mean ranking pi is like the average position of C minus lambda D is at most position of like here also the position of a candidate C in a pi ranges between like plus minus lambda t around its average position. So here the pi cardinality of pi is upper bounded by 4 lambda d, and the runtime is like without a significant increase, it is b equals to 16 to the power lambda d. These are the references. Thank you. Yes. Like we have not tried that, but we need to see. Like this is like we want to output not a single ranking, but a set of rankings. In this, yes, yes. Yes, on the parameter. Yes, we have to see this. Yes. Thank you.
Any other question?
Okay. I will fill you. Sure. Oh, please.
The next speaker is Jim Marley, the background of monitoring geometric sensing graphs, XML graphs, boundary, complexity.
Good afternoon, everyone. My name is Mami. Actually, I am coming from Myanmar, but now I'm studying the PhD of mathematics. I did the work in India. So today I would like to present about the monitoring AGO data set in graphs, extreme graphs, bound complexity. So this work we are joining with have forgot PM Masi, Abhisanti, Axen, X Taruni, and myself. So actually, this monitoring AGO data set is very useful in reality. For example, network monitoring field. So we can see in this diagram, there is computer devices and network connection between them. So we can consider sometimes a network failure. So that time we can say we need to detect where is failure, where is failure like this. Okay, suppose there is two devices and between these two devices network issue. Then we need to think about where it is failure. Then we have to consider the distance between those devices. Okay, so for this we will consider by graph theory. So all of devices we will consider as the particles, and between this network connection we will consider as the edges. So now we will consider for before we consider for monitoring AGO data set, we need to know what is monitor and H? So monitor and H mean if and HE, so which is the which lines between two vertices U and V. That time we can say U and V monitor and HE. For example, this is our graph. So we can see an HE. So this HEX, this HE lines between all shorter path between U and V, right? So this we will consider this H is monitored by U and V or not. Then we will remove this HE. Okay. Then we can see the distance between U and V will be increased. So then we can see this HEX monitored by U and V. Okay. So now we will consider another graph. Suppose all of these edges are shorter path between U and V. Then this HEX monitored or not. Okay, so we will remove this HE. Then we can see the distance between U and V didn't changes. Okay, so that's why this HE is not monitored for this graph. Now, to be clear for you, I would like to explain some example. So first, in parts, how many images set? Okay, how many image number means the minimum number we will consider. Minimum numbers of vertices will be should be monitored for all ages. Okay, so then if we will take middle vertices, suppose 2, 3 like that, then it cannot be monitored for all ages, right? So we need to consider for n vertices. Then let us take 1 and 4. Then it will be monitored for all ages, right? So that's why in every part, image number is 2. Then how about in tree? So in this tree, we can take all of pendant vertices. So if we do not take all pendant vertices, we will take 6 vertices 6 and 7. Then what will be happen? 6 to 7 paths will be monitored, but it is not monitored for 4 paths, right? So that's why we need to take all of pendant vertices in tree. So then we will think about for cycle. So how about cycle? In cycle, okay, let us take 2 vertices. So I would like to say 2 and 5. Okay, then what will be happen? This suppose 21H. Okay, this 21HX, it is line between 2165H path, right? But it is not this 21 didn't line between 2 to 5, 2, 3, 4, 5 paths, right? Then we cannot say it is monitor. That's why in this cycle, for cycle, we need to take 3 vertices. So now we can see every edges are monitor, right? So that's why monitor, so for cycle, every cycle, but except or C4. So this is MEG, it's 3. We can see like this. Then what is complete graph? Okay, so for complete graph, we need to, I think it will be easy to observe because every vertex, between every vertex has distance 1. And after that, there is unique shorter path, right? So that's why every vertices are included in the MEG set. Okay, so that's why we can say MEGs of complete graph is every vertices. Now, the last year CALDAM conference, focused on other they observed monitoring a geodata set in graph. In that paper, they observed about geodata set and a geodata set, strong a geodata set, MEG. MEG means short terms of monitoring a geodata set. Okay, so in this presentation, I do not want to explain all of definition. I will explain to MEG. Okay, so what is MEG? Suppose S is the subset of vertices of G, and we are already known and HE lines on shorter path between U and V, all shorter path between U and V. Then we can say UV monitor HE, right? So for every HE of G, there is a pair of vertices UV of X that monitor E. That time we can say this X is MEG, right? MEG set. So in that paper, they mention some notation such that geodetic number. Geodetic number they denoted by G, and which is the minimum cardinalities of geodetic set. And a geodetic set, a geodetic number they denoted by EG, which is the minimum cardinalities of a geodetic set. And strong a geodetic number also they denoted by SEG, which is the minimum cardinalities of strong a geodetic set. So now MEG. So for monetary age geodetic number also they denoted by small MEG, which is the smallest side of an MEG set of G, right? So now for this our work, so we will take this same notation only, okay? So this parameter, all of parameter, we observe first. We observed about relation between all parameters. So for this, we get one result. So this is, you can give any positive integer starting from 4 to increase sequence order. Okay, so then we can construct like a graph GAVCD. Let us get the name GAVCD. Then we can search geodetic number is A geodetic number is B, and strong A geodetic number is C, and MEG is D. Okay, so actually we need to do some construction, but I do not explain about today. Okay, so now we can consider characterize the graph G having MEG X numbers of vertices. So for this case, in the last year, only so monitoring a geodetic setting graph that paper only. I focus on other. They have result. Okay, so that result is for complete graph, a complete multi-party graph, hypercube graph. For this graph, every vertices are included in MEG, right? So that's why this is already got their result. So now after that, they ask in that paper, one question they ask. So this is open question for that paper. So what are the graphs are graphs with MEG X numbers of vertices? So for this open question, we need to study for this question. Then we have another question. So this is what are the vertices that need to be in every MEG set? Okay. So for that question, we have answer. So this is our answer. Suppose Vx the vertex, okay, vertex of graph G, and there is there is this U is belongs in neighborhoods of V, and there is into two parts UVX. This into two parts UVX is we can say if and only if. Okay, if Vx belongs in every MEG set, then if and only if this UVX is part of full cycle. Okay, so now because of this theorem, this theorem is our question answer. So then because of this theorem, we can answer their question. So their question we can answer MEG X numbers of vertices. Then if and only if for every vertex V belongs in vertices of G, there is this U belongs in neighborhoods of V, such that any into two parts UVS is part of a full cycle. Okay, so now we can observe one thing. See here has we are talking about C4, right? If the graph, the given graph have no C4 graph, then what will be happen? The graph at least at least 5, right? So that time we can say numbers of MEG is numbers of vertices. We cannot say like this because cat is at least 5. That's why we can say upper bounds of MEG is n minus 5, right? Okay, now now we can consider for upper bounds of MEG for higher cat. So for this case, suppose G is a quadratic graph having minimum degree at least 2, then G has n vertices and get G. This G should be greater than or equal to 5. Okay, because we are considered for higher cat. So actually I should mention, okay, no? So I didn't mention because I want to talk by mouth only. So MEG is less than or is equal to 4n minus G plus 1. Now, we will consider for click send and subdivision. Okay, this click send and subdivision, I would like to present about effect of MEG only. Okay, so then first one is suppose G1 and G2s are click that time we observed MEG of G1 plus MEG of G2 minus 2k less than or equal to MEG of G1 k clicks and G2 less than or is equal to MEG of G1 plus MEG of G2. Okay, so this is for k clicks. Now we will consider for subdivision. So subdivision is also if G is a graph. So every edge of G, we will do subdividing by L vertices. So this L is at least 2 vertices. Okay, then we will get the result. So this is MEG of original graph G divided by MEG of this resultant graph. Resultant graph means after subdividing. Okay, so it is including in bundles of 1 and 2. Now we will consider for computational complexity. So in this part, we need to recall something. So this is in 2023, monitoring age data set, hardness, and graph products. So in that paper, John Hasley Grave, he observed about the decision problems of data mining for a graph G and the MEG numbers of MEG is at most natural number k. Okay, so which is incomplete. So he observed like this, and after that, in that paper, he proved by reduction from Boolean such problems to MEG problem. Like this, he proved. Now, our work we will prove by reduction from vertex cover to MEG, right? So that's why we need to now. Okay, now we will go for our main results in this session. So our main result for this session is MEG set problems X and be complete even for 3 degenerate 2 impulse graph. Okay, so this theorem, before we prove, we need to think about, I already mentioned, we are thinking, we will prove by relation from vertex cover to MEG. That's why we need to think about for vertex cover. Okay, so then we have to construct something. Suppose G is a graph, and this graph G, every edge we will construct. Okay, let me construct like a, for example, P3 graph. Original graph is supposed P3 graph. This is for example. Okay, so a P3 graph, then we need to construct every edge of this P3 graph. So first we will construct every edge, we will add 4 paths such that A to A prime, A prime to E prime, E prime to B prime, and B prime to B, like this. So every edge we will add. Then we can see this new vertices. So this new vertices, we will add one pending vertex in each vertices, like this. Okay, and after that, we will add another one more neighborhood like this, common neighborhoods of A prime and B prime, like this every like this B2 prime and C prime. Okay, we will add, and this neighborhood of vertices Y. Then on this vertex also we will add again one more pendant vertex like this, and after that, originally this P3 graph, we will add one universal vertex like this. This universal vertex also we will add one more pendant vertex like A star. Okay, so then our construction is now completed. So in this graph, we can say this is graph G. I give the name G graph. Okay, so then this resultant graph, we can see all of pendant vertices. Let me take a set. Okay, Z is equal to set of all of pendant vertices, and if we will give the monitoring minimum monitoring age this number, suppose M. Okay, so not number set. So M. So then M minus Z is the vertex cover. right? So the vertex covers of original graph, not a resultant graph. Vertex covers of original graph. Then now we can verify. We can easy to verify our MEG set problem X and be complete because we can consider by polynomial type, right? So then by checking between two vertices, the distance between two vertices, then we can say this is our theorem already satisfied, right? So, but we have some open problems. So we don't know yet. We don't know for MEG problem in approximation and parametrics complexity. Okay. So in this presentation, I presented about relation between network monitoring parameters and characterize the graph G having MEG its numbers of vertices and MEG for the higher gap and effects of click send and subdivision, computational complexity. Okay. Thank you. Thank you so much. Graph product is already have result, some result, not our work, it is previous work. Yes. Thank you so much.
भाई बहुत लोग कल रात के लिए गई हुआ किसी का इतिहास कहाँ कौन खाली कर रहा है
Hello. Good afternoon, everyone. I am Tanveer Kaur. I am here to present my paper, Distance to Dispersion with Termination by a Strong Team. This is a joint work with Dr. Barun Gorain and Dr. Kaushik Mondal. This is going to be the outline of my slides. We'll begin with the introduction, followed by the literature overview. Then we'll discuss something about the model we are working on and the contribution given in the paper. We'll list some of the high-level ideas of the algorithms, followed by the future works which can be looked upon. And finally, we'll conclude with the references used for these slides. So the dispersion problem is a very classic problem and it has been worked upon extensively in the past. The problem says that if you are given an initial configuration of k less than equal to n mobile robots on an n-node anonymous graph, the robots need to reposition themselves in such a way that each node should contain at most one robot. Now the question is that if we impose some extra constraints on this problem, then what happens? So recently this problem was introduced, namely the distance to dispersion problem. In this problem, basically, there is a constraint which is introduced, that is no two robots can settle at adjacent nodes. Basically, the problem statement is given a set of k greater than equal to 1 robots that are placed arbitrarily in a port labeled graph with n nodes and m edges. The robots need to achieve a configuration where each robot needs to settle such that it satisfies following these two conditions. The first condition is no two adjacent nodes can be occupied by the settled robots. And the second condition is a robot can settle in a node where there is already a settled robot only if there is no more unoccupied position left, satisfying the first condition. So for example, if this is the initial configuration where 5 robots are placed at this node, this is the configuration after dispersion is achieved. Basically, there is no constraint. We just want that at each node, at most one robot can settle. Yeah. This is the distance to dispersion configuration. Here, if a robot is settled at this node, no robot can settle at this particular node. The only position, robots are compelled to be settled at these nodes then. So existing results which were given by Kaur et al. They gave an algorithm for rooted configuration. The time complexity achieved by this configuration was 2 delta times 8m minus 3n plus 3, provided the memory with the robots was big O of log n. They didn't require any global knowledge of any of the global parameters, and also the algorithm achieved termination. They also provided a lower bound on the number of rounds, that was omega of m delta. Further, Chand et al., they gave an algorithm to compute minimal dominating set. So minimal dominating set is also a maximal independent set. For the problem of distance to dispersion, if we have sufficient number of robots, we can achieve maximal independent set in the graph. So this is a little related to our problem as well. For the rooted configuration, they were able to achieve an algorithm that used big O of m time complexity. And for arbitrary configuration, they gave an algorithm that required big O of L delta log lambda plus NL plus m time complexity. Here, delta is the maximum degree of the graph. L is the number of nodes at which initially more than one robots are present. Basically, they are also known as multiplicity nodes. And lambda is the maximum ID length of the robots. A minimal dominating set is also a maximal independent set. Means for a graph, if we are able to achieve minimal dominating set, that is also a maximal independent set. This is so both the algorithms, they require prior. So both these algorithms, they require prior knowledge of all the global parameters that include delta, lambda, as well as n. So basically our motive was to study the power of a strong team. A strong team means using more number of robots basically, and to provide a solution for arbitrary initial configuration, since for the problem of D2D only for rooted case, the algorithm was provided, and to achieve a solution without any prior knowledge of the global parameters. The setup of or the model which we worked upon was the graph consists of n nodes, m edges. The graph is arbitrary and anonymous. That is, the nodes do not have any label on it, and it is port labeled. So each edge has a unique label from 0 to the degree -1 of that node. And if an edge is given two port numbers, there is no relation between those numbers. The robots, we assume k is strictly greater than n. They have unique ID from 1 to n raised to the power c, and they can communicate. The communication is face to face. That is, if more than one robot, that is, two robots are present at a node, they can communicate with each other. And also, the robots have memory, and the rounds are synchronous. So we gave two algorithms, one for the rooted configuration and the other for arbitrary configuration. For both the configurations, the memory used by the robots was big O of log n, and they do not require any global knowledge. The time complexity for the rooted configuration is big O of m, and for arbitrary configuration, it is big O of pm, where p is the number of multiplicity nodes. Yes, we assume the graph. Both the algorithms achieve termination without the knowledge of any prior knowledge of the global parameters. So, giving the high-level idea of the rooted configuration, basically we divide the algorithm into two parts. One is phase 1 and the other is phase 2. In the phase 1, we achieve dispersion on the graph, and in the phase 2, we convert this dispersed configuration into our desired D2D configuration. So since we are assuming that k is greater than n, so we have at least one robot which is extra, means it does not get any position to settle at during the dispersion. So at least one robot finds no position to settle at an empty node in phase 1. From that, we can conclude that that robot traverses through the graph and finally reaches to the root node from where the dispersion started. So at that particular time, the robot that settled at the root node can detect that the phase 1 or the dispersion is now achieved. Now we can move on to the second phase of the algorithm. So this indicates the completion of phase 1 and phase 2 is initiated. In the phase 2, what happens is the robot that settled at the root node, let us denote it by rmin, it sets its variable rmin.phase equal to 2, which basically indicates that the second phase has started. So it begins the traversal of the graph via the tree edges, and it reaches the node one by one. After reaching sequentially to the nodes, for each node, it tries to take decision for that node. The robot that is settled at that particular node, it traverses and decides whether to permanently settle at that node or to leave it or vacate its position. Graph is not a tree, but after we achieve dispersion, we can have a parent-child relationship that a tree is formed with which we can make use of the tree edges. Since this is the rooted configuration, so all the robots are initially placed at one node. So that we assume is the root of the graph. Yeah. Yeah. So there is a parameter that is stored with the root node, which represents that it is the root. So here we are basically working upon the power of a strong team. So we are assuming k is greater than n. So to gain information of the tree edges, since the memory by each robot is only big O of log n, and to store the information of all the children of a robot, the memory required may be delta log delta, which can in worst case be n log n. So to gain information of the tree edges, we employ some dedicated rounds. So in the dedicated rounds, what happens is in the first dedicated round, the robots execute one round of phase 1. In the second dedicated round, the robots that settled at even distance from the root node, they move towards their parent. In the third dedicated round, the robots that are settled at odd distance, now they know that these all are my children. So from this information, they can now decide with which child it has to move. Similarly, in the fourth and fifth dedicated round, the robots that settled at odd distance now move towards its parent. And in the fifth dedicated round, the robots that are settled at even distance now know their children. So in the sixth dedicated round, finally, the robots execute one round of phase 2. So our algorithm is basically running in iterations. This is the first iteration in which 6 rounds happens. Suppose we are at the 10th round. So that is basically 10 mod 6. So the task which is allocated for the fourth dedicated round happens in that round. Now what is the function of the robot rmin? Rmin is the robot that settled at the root node. So it moves through the child pointer of each settled robot one by one, unless it reaches a robot RU, which has no further child to move. Now, the robot RU, it decides to either settle at its original position or to move to a neighboring node that has already decided to settle permanently at its node. The robot rmin, on the other hand, decides to wait delta V, where delta V is the degree of the node where RU is originally present. It waits for these many rounds at that node, unless the robot RU, it is taking its decision whether to permanently settle at that node or to not to settle at that node. So if we look at an example, this is the initial configuration where 6 robots are present at V1. After the dispersion is achieved, let us suppose that these red robots are the settled robots at those nodes and green robot is the robot rmin. Now, after the last robot, it came here, the robot rmin, this green robot, it knows that phase 1 has now come to an end. Now it has to start execution of its phase 2. So in the second dedicated round, these 2 children move towards its parent. So deterministically, the green robot, it decides that from 0 and 3, it has to pick the minimum one. So it picks 0 and moves to V3. In the next round, means in the next dedicated round, V4 and V5, the robots that were settled at V4 and V5 move towards its parent. And the green robot now knows that 2 and 0, port number 2 and port number 0, are the children of this node V3. So it deterministically chooses the minimum of them. So port 0 is chosen and green robot reaches here. Now further, it has no child. The dotted edges represents the non-tree edges and the darkened edges represent the tree edges. So it has no child. So the green robot waits here for 2 delta rounds, while this red robot, it moves towards all its neighbors and checks whether we define a parameter called perm settled, let's suppose. So no robot has taken its decision. So this robot moves through its neighbors and finally it sees that no robot has decided to settle at its position. So it settles here permanently. This blue color represents that it has decided to settle here permanently. Now, the green robot returns to this position. Now, 0 has already happened and this decision for this node is already done. So, in the next dedicated round, this robot moves towards its parent and when it moves towards its parent, the green robot knows that it has now to move through port number 2 and it has no further child. So, decision for this robot now happens and this robot, it traverses through all its neighbors and sees only neighbors are now V3 and V1. So both have not taken their decision yet. So this robot decides to settle at its original position. Now in the next round, the green robot, it moves to V3. When it moves to V3, it has no child left whose decision is not yet taken. So the robot, now it is the turn of the robot that settled at the node V3 to decide whether to settle at its original position or not. So it traverses through port 0 and sees that there is a robot that already permanently settled here. So it no longer needs to traverse all its ports. So the robot that settled at V3, it moves through its port 0 and settles here permanently. Now, on similar pattern, the green robot reaches here, then here, decision for this is taken. Then it returns to V1 And finally, V1 has no robots left whose decision is not taken. So the robot that settled at V1, it moves through port number 1, and those 2 robots that finally settles here. So this is, we are using this technique, we are able to achieve D2D, distance to dispersion, in the robots, where these blue robots are representing that they are permanently settled now. And the distance between any 2 robots we can see is at least 3. At no 2 adjacent nodes, any robot is settled. So from this, if G is a port labeled undirected and connected graph with n nodes and m edges and maximum degree delta, so k greater than n robots are initially placed at a single node of the graph, and robots have no prior knowledge of the global parameters. The robots achieve D2D on the graph with termination in or big O of m rounds with big O of log n memory per robot. Now for the arbitrary configuration, when the robots are arbitrarily placed in the initial configuration. Now the challenge is how can we achieve, since there are different groups present, different groups may be present initially in the graph. All those groups, they run their DFS, they start running their DFS. Our main motive is that by the end of the dispersion, we have one tree, or corresponding to one DFS, we have a tree formed so that we can use the phase 2 of the algorithm discussed previously. This algorithm also runs in phases. So phase 1, dispersion is achieved, and phase 2, we convert the dispersed configuration into desired D2D configuration. Our target is to merge DFSs in such a way that at the end there exists exactly one DFS tree in the graph, and finally convert the dispersed configuration into the D2D configuration. So basically what happens is each group has a label, and that label can be the minimum ID robot that is present in that group. They start running their DFS as and when a smaller labeled DFS meets a settled robot with larger label, it includes that settled robot into its DFS tree, that settled robot. Whereas on the other hand, if a larger labeled DFS meets a robot of with smaller labeled settled robot, it stops the execution of its DFS and tries and sends all its unsettled robots into that DFS. So basically, subsumption is happening. So with using the technique, we can ensure that by the end, the minimum labeled DFS will persist in the graph. So each DFS traversal is associated with a label that corresponds to the minimum ID of the group. When groups of unsettled robots from 2 or more DFSs meet at a common node, minimum ID robot will settle at that node, and unsettled robots join the DFS. And if the unsettled robots of DFS L meets with the settled robot of DFS M, if L is greater than M, here L and M are representing the label. If L is greater than M, then the unsettled robots of DFS L follows to reach the head of DFS M and extend the DFS of M further, because we want the DFS with the smallest label to persist in the graph. And if L is less than M, then the settled robot of DFS M becomes a part of the DFS L by changing its label and the parent pointer. For example, in this example, 4 red robots are there. At V7, 2 green robots, and at V5, 3 blue robots are there. And let us assume that the label of this red is the smallest. So red is less than G is less than B. So when these triangle robots are representing the settled robots, when dispersion is happening, these red robots start the traversal through port from V1 to V2 and then to V3. And green settles at V7 and V6. Blue, it settles at V5, then V4. And then when it reaches V7, it sees that there is a smaller labeled settled robot present at V7. So it changes its label to green and reaches V6, means it basically tries to reach to the head of the green DFS, while the red is continuing. So in this example, in this configuration, the green DFS is extended now, while the red unsettled robots are left. And finally, when they meet at V4, this DFS is constructed that only that is only corresponding to the minimum labeled DFS that was red. And finally, this darkened edges represent the tree edges, while the dotted edges represent the non-tree edges. And these are all the pairing pointers corresponding to them. So if G is a port labeled undirected connected graph with n nodes, m edges, and maximum degree delta, k greater than n robots are initially placed at p multiplicity nodes, and the robots have no prior knowledge of any global parameters. Algorithm solves D to D with termination in order of PM rounds, and order of big of log n memory is required by each robot to run the algorithm. So the future works, it would be interesting to do a lower bound study of D2D starting with k greater than n robots, analyzing and improving the time and memory complexity to solve the problem of D2D with k less than equal to n robots is also another part which can be looked upon. Finally, solving D2D in the presence of faults is another direction of study. These are the references used for my slides. Thank you.
Sanjay. Hello. Am I audible? Yeah. Okay. Yeah, I was as part of my master thesis in IIT. Yeah. Yeah. So actually, this was my master thesis with Sunaina Petro under the guidance of Rajat Mittal in IIT Kanpur. So I'm like to take you through the same journey we took through the complexity measures regarding symmetric functions. So yes, first of all, when we started the thesis, we were particularly interested in the query model because it very elegantly explains most of the quantum algorithms like Grover's and all, and it had very solid and well-studied lower bounding techniques. The major ones in Ronald A. Wolf had already formulated the quantum query complexity for total symmetric functions, like completely, and one of the major lower bounds, spectral sensitivity, recently was found to be a very easily calculable, a lower bound which can be easily calculated for the adversary methods, which is a lower bound for quantum complexity. So we were looking into adversary bounds for total symmetric functions and also the quantum complexity of some partial symmetric functions. So we'll be rushing through some of the preliminaries because of the time. Okay. One of the major things about Boolean functions we need to know is the sensitivity. So sensitivity is for an input at an index I, it is sensitive if just by flipping that index you'll get another input which has a different function output. So any algorithm should be able to distinguish in between these two. Like that will be the toughest. They are easy to get confused with. So the sensitivity graph, it represents the sensitivity by putting all the vertices, all the inputs as vertices, and the edges represent if it's a sensitive edge or not. Like for the 2-bit ORs, it's easy to get confused between 0, 0 and 0, 1, looking very similar but have different function outputs. It's okay to get confused between 0, 1 and 1, 1 because it's anyway giving the same output. So yes, in the quantum query model, we'll start with a 0 vector, which is subjected to a list of queries, which acts as matrix multiplications. And we get the final output vector, which is expected to be perpendicular for different functional values, 0 and 1. Thus distinguishing between the. So here Vx represents the whole quantum algorithm, which is a series of oracle queries. We query the input using oracles, and it's a unitary oracle, which we have unitary operators along with. Now the adversary method was the major lower bounding technique we explored. It was formulated by Ambani's. It it basically looks through a set of two sets of inputs, one giving function 0, one giving function value 1, and it studies how well or how much steps will be required for the quantum algorithm to tell between all of them, like not get confused between two outputs. Now it gives a lower bound of such. Here, yeah, we cannot explain the whole thing. It's kind of out of the um, so the detailed one is given in the literature. So M and M dash, they more or less say how many the function values are, how many different outputs can be possible with a different function value, how many inputs with a different output value, and the L and L dash gives the like the query, the estimate of how much you can tell by looking at one bit. So if you cannot tell much by looking at one bit, you will have obviously have a lot more of queries to do. Many variations were introduced for this, including spectral adversary, min-max formulation, and all that. All the formulations are identical in the positive adversary world. Yes, so this was a major part of my work in here. It's the spectral sensitivity. The spectral norm of adjacency matrix. The adjacency matrix, if you can recall, it is a way of representing the sensitivity graph. The adjacency matrix of the sensitivity graph, basically. So this adjacency matrix basically shows it's the spectral norm. It basically shows how hard it is to for an algorithm, for a query-based algorithm, to distinguish between two inputs which have different function values. The spectral norm is counted as the maximum stretch the adjacency matrix can give to a vector when multiplied. So what is the maximum magnitude you get when it's multiplied by a unit vector? This was found to be a lower bound to this adversary method. And this is much easier to calculate than the normal adversary method. So yes, approximate counting was another tool used here. So here in approximate counting, you basically count the Hamming weight of an input. You try to estimate the Hamming weight, like count the ones or count the zeros. And it can give an approximate count, like with a slight error of delta for any input t, like the n count. The result it gives will be in the range 1 minus delta into t and 1 plus delta into t. So this approximation can be done very efficiently in a much less number of queries than usual. So yes, now with all these preliminaries, these were the tools in our belt. We were going into the results which we were able to accomplish. Spectral sensitivity for threshold functions. Threshold functions are the most simple type of symmetric functions we can see, and we use this to actually gain more insight into the adversary bounds of all total symmetric functions. And then we have the quantum complexity of gap majority, which was where the approximate counting came to use. And then it's a corollary relation we found for now noisy randomized query complexity. Okay, threshold functions basically is the okay, it's basically you can always represent symmetric functions in a line because it's only about the Hamming weights. Symmetric function only is about the Hamming weight. The permutations doesn't matter. So from a Hamming weight 0 to k, it will take the value 0, and from 1 to n, it will take the value 1. So this is if the k is put to k is put as 1, it becomes the over function. If the k is n by 2, it becomes the majority function. And we deduce the vector vk, which will give the maximum stretch possible for that adjacency matrix. I'm not going to go into the details again, out of the scope currently. So yes, this maximum stretch was found to be root of k into n plus 1 minus k. Now this is already the computable upper bound for the spectral sensitivity. So this stretch is the maximum. You cannot go better than this. And also in case of threshold, we can generalize to the left side, k less than n by 2, because k greater than n by 2, you're looking at the equation, you can say it will give the same output. So we are only looking into k. When k less than n by 2, it is of the order nk, the threshold. And by the Ronald-Wolf's quantum query computation, this is the quantum query complexity for threshold functions already computed. Now with that, we have already seen what threshold functions can be, how complex it can be, went into total symmetric functions. So total symmetric functions the way we like to look into them was the same way. This was the same concept used by Ronald De Wolf. In between, it's just how far from n by 2 you can say the function is constant in this gap. Tf to n minus tf, the function is constant. So here we are looking for the minimum tf where this is true. So you can say that the function value changes either at tf or at n minus tf, the function value changes. Now looking into this, symmetric function when written like this, it looks to be like a linear combination of a lot of thresholds. Like at some points, at some Hamming weights, the function value changes. Before that it's 0, then it changes to 1, or before it's 1, then it changes to 0. So the adjacency matrix, when you write the adjacency matrix for this one, all the sensitive edges were the sensitive edges for one of the constituent thresholds anyway. So the adjacency matrix for any threshold any symmetric function, any total symmetric function, can be written as a sum of adjacency matrix of some thresholds. Which means now all these are all positive matrices. It's all 0 1s, it's all Boolean matrices. So the spectral sensitivity for this matrix cannot be less than the maximum ones in the constituents. So it will be greater than or equal to the largest one. Looking at the equation for Tn, we can Nk for threshold, we can say that the one nearest to n by 2 will have the largest value for the spectral sensitivity. Hence, we know that this spectral sensitivity same as adversary. Adversary is lower bounded by n into Tf here, because spectral sensitivity is n into can only be greater than n into Tf. So here it is adversary function has a lower bound of n into Tf, but again it's already computed by De Wolf that this is the quantum query complexity, the same value which we have obtained. It was already computed as the complexity, quantum complexity in a query model for any total symmetric functions. And afterwards, we went into a different formulation for the adversary bound. This time, upper bounding using the adversary, which is the min-max version. And this min-max version formulation, it appeared to be same as the certificate gain complexity. It is detailed studied in a paper by Saurav Chakravarti. You can go into the details there. Again, the proof is out of scope of this discussion. So we saw that both have the same, very similar formulation and the same weight function, which we use for this formulation of min-max, can give the optimal output for the certificate gains also. The only difference was the square root and the constraints, but that is not being affected. The same weight function can give the optimal output for both. Thus, we came to the conclusion that the square root of certificate gains and adversary are tightly bound for any total symmetric function, and that equals the already known quantum query complexity. Any questions still here? Okay. Okay. Then then we went to try to take our intuitions to a little more. What can we say about a little more about uh, symmetric functions? And we saw that there is a category less explored, which is partial symmetric functions. Partial symmetric functions don't give an output for every input you can give. It is only for a certain set of outputs. So major partial symmetric function we found was the gap majority. It's part of some interesting results. So we decided to explore gap majority a bit. So yeah, so the first we try to give a upper bound, an upper bound which is through only possible through an actual algorithm. So the quantum algorithm through approximate counting we discussed earlier, because here the how it is basically formulated in gap majority, the function value exists only in these 2 points. Everywhere else it doesn't matter. Now, looking at our former proof, which we did for spectral or quantum complexity, or going by the De Wolf method, it will still take O of n, theta of n kind of steps to complete it in De Wolf method. But we were not sure if that was required, because this middle portion doesn't really matter, nor the others. So This is majority function. Majority function is the threshold function with the maximum complexity, but still there is a huge gap. So we wanted to know if we can make use of that gap to make it even simpler. Like a known function, majority is a known function, but with the gap doesn't become simpler. And then we so that to count up to this without overlapping, like we can give an approximate count for both these inputs, and there'll be a 1 minus, we can give a delta is 1 minus root, delta is 1 by root n. So this delta will mean when we try to count n minus 2 n by 2 minus root n, it will have an upper limit for what it can give, and there will be a lower limit for the other one. We just wanted to make sure these two didn't overlap, and for this given error probability it didn't overlap, and the complexity surprisingly was just root n, something that could have taken us n on the order of computation in the order of n by a de Wolf method, by a known method. So okay, then the lower bounds basically came from the general Ambani's theorem, because you cannot use sensitivity for partial symmetric functions. Sensitivity doesn't exist because there are no, in case of gap majority, there is no two inputs which just differ by 1 bit. The outputs differ by 2 root n bits. So for this particular function, we we found the relation xy in such a way that the bits set in x are also set in y. With that relation, we obtained the mm dash and l dash, which resulted in the lower bound, which is the same, root n. Thus, we were able to say that the quantum query complexity of gap majority is for definite root n, cannot be lesser, and it need not be higher than that. So the gaps in partial symmetric functions does seem to have give a computational advantage. A similar function in total symmetric, you will have to compute a lot more. So in case of partial, it gives an advantage here. So yeah, and we ended up with a corollary. As I said, there were some interesting results with gap majority, which is why we looked into that. And we have these two relations already. Connecting quantum query complexity of any function, any total function, with the gap majority complexity. Now we have the gap majority complexity, so we can say this generic result that noisy result, quantum query complexity cannot be more than noisy randomized complexity into root n. These were the 5 results which we have included in the paper. And we also did a lot more of digging into complexity and into sensitivity, block sensitivity, and certificate measures of all Boolean functions, all symmetric functions, which is included in the extended version. So if any of you are interested, please look into that. The extended version is also given in the abstract of the paper. Yes. So this was the final result we arrived at, where the computational the certificate game complexity with a private coin, which was formulated by Saurabh Chakravarti, was equivalent to the square of the adversary method formulated by us, the thesis. And yes, we do have a lot of future work in mind. One of it is we already saw how majority changes from order of n problem to order of root n just by introduction of a gap. So how we can we are trying to extend it to different threshold functions other than majority. See how the gaps make it simpler for all threshold functions, and if possible, that can give, like, threshold functions gave a much efficient computation of uh, all total symmetric functions. The gap thresholds may be able to give a lot of insight to a generic algorithm for any partial symmetric function, which is a future work. And yes, and adversary bound studies for transitive functions and cyclic functions, which is already started in some works by Saurabh Chakravarti and others. So we're planning to use this extra insights we have gained through the adversary into this. And yeah, the literature, which of course it was at least 40 papers, which the reason why we reached it here, but the major ones, these 5, you can look into the details in the proceedings paper itself. Thank you. Yes, sensitivity conjecture was proved by Huang, and this paper by Aronson and David and this one, they followed from the same. Like we use that idea of hypercubes. They use the hypercube idea to reach a better formulation of the spectral sensitivity, how it can lower bound the adversary methods, all the adversary methods. So we were following on the same intuitions which they've gained from the hypercube problem. And yes, initially it's basically which were Hong. Yeah, it's not directly related to Hong, but Huang's result is the reason why we have the Aronson paper, which is what gave us the insight for spectral sensitivity, how it can be used. So basically, spectral sensitivity was a easier way to count how sensitive this function is. Like the sensitivity, which we explained here in the sorry, one of the initial slides. So as I explained in this, so here the reason what a quantum algorithm should do is not confuse between two inputs that look the same, almost the same, but but have different outputs. So sensitivity is a measure of that. Sensitivity large means there are inputs which look very similar to other inputs, but have different outputs. So we need to have the less number of queries. Like here, the T should be minimum, but it should not confuse. So spectral sensitivity gives a wider range, like a kind of a better insight as to how much we should do to lower bound more than sensitivity. Sensitivity cannot be directly used as a lower bound. So yes, that was the leading motivation what led to all these results. Anyone else? Thank you.
Hello. 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 Okay. Yes. So is it good? Am I audible? Okay. So thank you for coming, everyone. So my name is Deepayan Chakraborty. So I am a PhD student, third year PhD student in France in Université Clermont-Auvergne, the first one here. So I will be talking about location domination type problems under this graph construction called Misielski construction. So this is a joint work with one of my supervisors, Annie Great, and two of our Argentinian colleagues. So I will start with an introduction of what these problems are, location domination type problems. So there will be some motivation and definitions. And then we will look at three particular types of these LD kind of sets that we work on this Misielski of graphs. And then I will conclude with some questions. So first of all, what is this property of location domination? So let's say you have a graph and I have marked some blue vertices and some white vertices. So basically the work of the blue vertices is to somehow monitor, let's say, the white vertices. Okay, so I want to somehow associate with every white vertex some kind of a string of numbers which are unique to each of these vertices, the white ones, so that I can, from these numbers, the unique numbers, I can differentiate one from the other. This is called separation, the property of separation. So, as a practical example, think of this as a building plan where you have like 10 rooms. This is like a cross-sectional area, and there are some passageways and doors like that. So you may have an intruder in your building. Okay, it can be in any of the rooms, and you want to locate exactly in which room the person is, so that you can identify and catch the thief. So one way to do that would be to, let's say, put some detectors in some of the rooms. We want to put detectors in not all the rooms, some of them. So you have to think of these detectors as some kind of radius 1 detectors, which can detect the presence of a person in the next room. So these detectors can do two things. Like if the intruder is in the room itself where the detector is installed, it can signal that okay, it is the intruder is in my room. Or if it is not, so for example, if the thief is in room 4, then it's the neighboring ones 2 and 3 which will kind of trigger some alarm and give a signal. So you can model this with a graph where every room is a vertex and you have these edges wherever there are doors, and we mark in blue the rooms where we want to put the detectors. And well, that's basically where the problem is now. I mean, you can forget about the plan. So what happens is, therefore, we get those numbers which I showed right at the beginning. So if the thief is in room 9, for example, then it's the 7 and 10 which will be triggered together. And from this combination, 7 and 10, which will, if these two alarms ring at the same time, you know that the thief is in room 9. So we have to pick this set slightly intelligently. So if, for example, there was an edge from 8 to 10, this particular set of blue vertices wouldn't work, because even 8 would have the same set of numbers as 7. It would have 7, 10 as well. So this particular set wouldn't work. So we have to exactly select what kind of, select intelligently where we want to put these detectors. So as you can see here, I was using 6 vertices as monitors, like 6 blue vertices, but we can do better actually. So we can actually pick 4 of them and still get unique numbers for each of the white vertices. So the idea, of course, as you can guess already, is to minimize the number of this blue set that we want to pick. So these are basically these numbers that get associated with these white vertices. These are, in this example, they are intersection of open neighborhood of all these white vertices with this set S, the set of blue vertices that I have picked. And this set S has this property that, well, I will come to the formal definitions. So it is a dominating set. In other words, it's kind of well spread out in the graph, okay? Covers every vertex up to distance 1. And of course, this separation property that I've, these numbers, the intersection of a neighborhood of 1 with S will have to be different from the intersection of a neighborhood of 3 with S. So this property of, this is called a separation property, but particularly this is called location. When you want this kind of distinct sets for each vertex, for all UV which are outside of the set, outside of S, okay? So we are only monitoring the white vertices. So, okay, just for some formal definitions. So an open neighborhood denoted by this symbol is basic of vertex V is all the vertices U which are adjacent to V, and the closed neighborhood is just the open neighborhood plus the vertex itself. We will call two vertices open twins if their open neighborhoods are the same, and we will call them closed twins if their closed neighborhoods are the same. In general, we use the term twins when two vertices are either open twins or closed twins. So in this example, the two blue vertices are actually open twins, and the two red vertices are closed twins. Okay. So what is a dominating set? It is a set S of a given graph such that the intersection of the closed neighborhood of a vertex V with S is non-empty for every vertex in the graph. Uh, Another way of saying this is that you're given this graph, you pick a set S such that every vertex outside of it has at least one neighbor in the set. Another variation of this dominating set is it is known by two names: dominating set or total dominating set, where if you replace this condition of closed neighborhood with open neighborhood, you get what is called a total dominating set. So again, another way of seeing a total dominating set is that it's not only a dominating set in the graph, but even the guys in the set S, they have to have a neighbor in the set S also. Okay, it's not just the guys outside of S. So, and there are some separation properties. I've already spoken about one in the example where you want these open neighborhoods in S to be different for all UV outside of S. This is called location. So if a subset S satisfies this property, it's called a locating set. In some problems, you may want to monitor all vertices, like we were only monitoring the ones which are outside of S. So it's the same thing is called open separating set. If the same condition, the separating conditions are imposed, but now instead of U and V outside of S, we want U and V to be in all the entire vertex set. And similarly, if you require, instead of open neighborhoods being separated, instead of that, if you replace them by closed neighborhoods, the corresponding set is now called a closed separating set. So these are three kinds of separation properties that have been studied classically. So again, to define formally what is a locating dominating set, the one that we saw in the example, is S will be a locating dominating set if it is a dominating set and it is a locating set. And an LD code will always exist because if you take the entire graph, that itself is an LD code. Actually, you can show that if it's a dominating set, the dominating set always exists, and even a locating set always exists. So these two will kind of combine to say that, okay, locating set, LD sets will always exist. This was first introduced by Slater in 1988. Another variation of this is what is called the locating total dominating set. As must be clear from the naming itself, we want the set to be also a locating set, but instead of dominating set, we want this to be a total dominating set now. So yes, they're also called identifying codes and locating dominating codes. So I'm using set just so it's clear that it is actually a set. So this will LDD codes, or here I have actually used codes somehow. I've used two terminologies. They will exist if G is isolate free, doesn't have any isolated vertices. That comes from the fact that it is a total dominating set. In a total dominating set, for a total dominating set to exist, you can't have a graph with an isolated vertex. So this was first introduced by Haynes, Henning, and Howard in 2006. Another variation, or the third type of problem that we will look at, is what is called the open locating dominating set. Here, you want the set S to be total dominating, but now instead of the location property, you want open separation property. So you are separating vertices by open neighborhoods for all vertices U and V, okay, in the graph. So this was also introduced by Sue and Slater in 2010. And OLD codes will exist if G is open twin free, because for open separation, you want the graph to not have any open twins, and also isolate free because it's a total dominating set. So these are the three main problems that we will be looking at. But other than that, this is a literature, like a table which kind of tells you about what other problems have been studied. So the first three are based on close domination. So these three sets are all dominating sets. These three problems, the sets are all dominating sets. And you have close separation, open separation, and location, all three varieties have been studied. They come under different names: identifying code, open separating. This is a new one which we have kind of introduced recently. And locating dominating is the one I just talked about. The last three are based on total domination or open domination, OD for open domination. And again, all three varieties of the separation have been studied. So this open locating dominating is the one I defined in the last slide. And also we talked about total locating dominating. So usually in these problems, we are interested in this particular kind of number here. So let me define what is an X number. X being any abbreviation of any of the names here actually. So for example, ID number, LD number. So what it is the minimum cardinality of all sets which are X sets of G. So if you consider all LD sets of the graph G, and you take the minimum cardinality, that would be the LD number. Similarly, LTD number and OLD number, like that. So that is the parameter that I'm going to talk about for these three problems. So, okay. So Michalski construction is what we look at. So we study these problems on Michalski's of graphs. So what is this construction is basically if you have some graph. So I've taken the example of a path because it's easy to draw. So basically you replicate all the vertices, the V1, V2, you replicate them by U1, U2, but you don't put edges from the original graph here. But you make, for example, if V2 is adjacent to V1 and V3, you make U2 adjacent to V1 and V3 as well. So you make U2 and V2 basically twins in this part of the graph, okay? And then you add this, well, like a partial universal vertex, which you attach or make it adjacent to every vertex in this layer that you have added. So similarly, this is an example of C3 with this Michalski. So this was first introduced by Michalski himself in this in a way to give an example that if you start with the triangle-free graph, you can make it into turn it into a bigger triangle-free graph, but without actually, but increasing its chromatic number by 1. Okay, so and we can ask the same. So basically, so the idea was to not increase the clique number, but increase the chromatic number at each iteration of this construction. So we can ask the same kind of questions, and in our setting, we were asking, what do these parameters, the X numbers, LD numbers, LTD numbers, do they increase, or what happens to them if you turn a graph into its Michalski? So, okay. So the first thing we wanted to look at, so here X by X I will mean LD, LTD, and OLD. So the question was, if you take the X number of the Michalski of a graph, does the Michalski, this number increase or decrease? So in general, it's not true that, if you have a graph as an induced subgraph of a bigger graph, then it's not true that the X number of the bigger graph will be bigger than the X number of the smaller graph. So for example, yeah, for if you take a 4 path, the OLD number of this is actually 4, because you have to take all 4 vertices to distinguish these two, which are almost open twins, except for this guy. You have to take it. And similarly, for these two, you have to take this one. And because this is a total dominating set, this one, so let's say you have taken those two, because this is a total dominating set, you want a neighbor of this in your set, and similarly you want. So OLD of P4 is actually 4. But if you attach something like this, then just taking these 3 is a good OLD code. Okay, so the code actually drops. So we were not sure whether, in general, what happens. Actually, the plan was in the beginning to do it for general graphs, but it turned out to be quite hard. So we looked at only paths and cycles, and we were able to prove that the X number does in fact become the X number on the graph plus 1. Okay, so it doesn't decrease. Okay, but okay, so what this tells us is this is a set of 3 results from the literature. So the LD numbers for paths and cycles were worked out in this paper by Bertrand, Sharon, Hudry, and Lobstein in 2004. Similarly, Henning and Rad had worked the LTD number for paths and cycles exactly. These are exact results. Sue and Slater in the paper where they introduced OLD had shown that the the OLD number for paths is exactly worked out like this. Is it's 2/3, 4 out of 6 vertices you have to take. So we had these results available from the literature. So basically, we can plug in these numbers here, okay, and so for paths and cycles, we have the lower bound with these particular numbers plus 1. So this doesn't really add much to what we already have, but it's just there from the literature. However, the cycles for OLD for cycles was not there in this paper, but it was there in one of the previous another conference paper. But while trying to do the same thing here, we found out there was some issues. The result was not correct, so we had to also correct that result. So now in this paper, as a side result, we have the OLD number for cycles, which are very much similar to paths, almost 2/3, but there are slight differences in constants. So anyway, so we also have corrected that result from the literature, and then of course added 1 to give the lower bound on the OLE numbers of Misielski of cycles. So, but as I will tell you more, you will probably understand that this lower bound is not very good, because there is a scope to improve this lower bound actually. So let's come to upper bounds, and this will make it clear why we need to kind of improve the lower bound. So now I talk about general graphs for some time. Okay, so it can be shown, and not very difficult to show, that if you take any graph, the OLD number of the Misielski is bounded above by the OLD number of the graph plus 2. So why that is because, so again, this is a general graph, but I've drawn a path because it's easy to draw. So if you start with this layer, this is a path. If you start with just the OLD number of this is a P10 actually. From the previous results, we know that we need 8 vertices for the minimum OLD set. So we have taken 8 of them. Now the thing is, what happens with these guys? So any 2 vertices from here have the same relation on this line, with the vertices in this line, as their counterparts here. Okay, so if any 2 vertices here are separated by other black vertices, those 2 will also be separated in this layer. Now, of course, we need to remember we are in OLD, so we are separating both white and black vertices. Okay, so there is no distinction now. So, but we also have to separate, for example, vertices from 2 layers. So in that sense, it's it makes sense to take this like partial universal vertex, because this one sees that and none of these vertices actually see that. So we take that, but of course we are talking about OLD, which is total dominating. So you have to take something from this layer for this black vertex to have a neighbor in the set. Okay, so this way, you can show that just taking any 2 vertices, this partially universal vertex and this one, kind of suffices to give an upper bound on the OLD number. So of course this translates to for paths and cycles as well. But the story is not the same when you turn to X being an LD or an LTD. Here we had to go to twice the X number on the graph itself. This is because now, again, we start with this minimum LD set, let's say, on this graph, the path on 10 vertices. So all the white vertices, the counterparts of all the white vertices are separated because these are separated on this line. But the black vertices which we had taken, we don't care about separating them, right? Because in LD, we were only separating the guys outside the black set. So their counterparts now, for example, this guy and this guy are not separated. In fact, they're not even dominated. Okay, so they have. So what you have to do is somehow separate these kind of things which are the counterparts of the black ones on the higher level. So one sort of mindless way to tackle this is to just include these whatever black vertex is there from the lower layer, you put up, you take the upper, the counterpart in your set. And it turns out that this works because we actually have this is tight, because if you have a star and if you turn it and look at its Michalski, what you get is this graph. And here in the LD set of any star, you basically have to take all but one vertices from here, because these are all open twins. They all have the same neighbor. So you can't leave one of the guys outside because they have the same neighborhood, right? So unless you take one of them from the two, there is no way to separate because they have the same neighborhood, the open neighborhood. So here you have to take n of them, and again here these guys are all open twins. So again you have to take, let's say, all but one. So like we have taken in the lower half here. So even if you leave this out, now the question is you have to dominate it somehow. So maybe it's good to take this vertex because it dominates these two, but also you have to separate them now. Okay, so either you take this guy or this guy or this guy. Okay, so anyway, whatever it is, we have to take 2n of them. So it turns out that this is tight. Okay, so this was for general graphs so far. So we asked, so for general graphs, we had the strategy of taking just the counterparts of these black vertices from down below. Then we asked, could we do better for, I mean, just if we take the graph now to be paths and cycles, okay, because that's what we are concentrating on in this paper. So it turns out that we could have a better strategy. So if we wanted to separate these two guys, instead of just taking one of them, what we could do is we let this guy be as it is, and we take, let's say, its neighbor here, okay, or here, okay. So, sorry, not here. Either this guy you have to take or this guy you have to take, okay. So I'm trying to take vertices from down below, okay. Even if you take vertices from up, you can sort of push them down. So let's say I pick this one. Then again, for this guy and that guy to be separated, you pick either this guy, this one, or this vertex. I again pick this one. So in a way, there is a strategy that you can give that for all these vertices which had this black vertex down here, you pick one guy to its right, and you pick like 2 out of 3 in this pattern. Okay, you can have other codes, but somehow you can always turn it into something like this, by shifting, and the numbers don't change at all. Of course, you have to take one last guy here because you have to. So this one and this one are not open separated, or let's say located here. If this is not taken, okay, because they are twins here. Okay, not twins, but this because this is left out, you have to somehow take this guy here. So at the corners, you may have to manage 1 or 2 things. Okay, so 2 out of 3 vertices on this line. Okay, so and that's what the numbers reflect. For paths, it is so if you break this n to as a multiple of 3, then you have to take like 2 out of 3 almost. And so similarly, the same story happens if it's a cycle. I mean, for a cycle, this vertex might be attached or adjacent to this guy. So instead of this guy, you could have taken this one. That way you would have completed this pattern here, 2 out of 3 on this line. But it's the same story. It's 4 out of 6. Okay, so it's the same kind of a ratio that we get. So here we actually improve because if you remember, the for paths is actually 2/5 the number of vertices. This was in the literature. So if we had taken twice of that, that would have been 4 out of 5. But here we do 2/3. Okay, so we kind of improve with the strategy. And similarly, the same pattern holds for LTD. So all this, the entire argument here was for location. Okay, so all this pattern that we got 2 out of 3 everywhere on the line was because we were trying to locate the vertices, and because LTD is also a locating set, we can do the same pattern here. Okay, we do the same strategy, but here we need to add one more somehow, because it's also a total dominating set. So for example, this guy is left alone. Okay, this black guy has no neighbor, so you have to somehow take one. Okay, in the case of a cycle, this one could have been attached here, and as I said, you could have left this one here and taken this one, but then this vertex would have been there with no black neighbor, so you had to take something. So anyway, it's a small technicality that because now it's a total dominating set, we have to take one more somehow. So yeah, so it's the same thing that works, but again, we kind of improve the bounds, the upper bounds. So yeah, that's more or less where we are. We looked at this for paths and cycles only in this paper. So as you can see, oh, by the way, I forgot to mention that we looked at these examples up to P something, I don't know, 15, 16. We didn't run them on computer, but we did them by hand. Turns out that these are like tight examples, okay? So somehow you have to increase the lower bound, which we haven't quite looked at in more detail yet, okay? So there is a room for that. And there is a conjecture that kind of comes out. I don't know if it's true, but it feels like. So what you have, in order to sort of locate these guys, like all pairs of vertices here, somehow you are creating this OLD code of this line here, okay, this path. And maybe you're taking one or two more just to adjust things at the end or something like that. So it turns out that the feeling is that for when X is LD and LTD, the number for the Misielski is going to be the OLD of the graph. Well, I mean, here I conjecture only for the paths and cycles because that's what this was. So OLD number of the path or the cycle plus some small constant here. So this is something that is kind of interesting, and one could look at maybe by increasing the lower bound. Okay, thank you. Yeah. Yeah. Yes. Mm-hmm. Yeah, it could be. It could be. Yes. Yeah, this could come in handy. Sure. In fact, we did try something like that at some point, but well, I think we didn't try harder. Yeah. Thanks. Thank you. This is correct. Hello. Okay, so I'll be talking about
this one of the classical problem called total coloring problem. And this is a particular class of graphs called complete multipartite graphs. So even finding the, okay, let's see the definitions quickly. So everybody knows what is a proper vertex coloring. So color the vertices in such a way that no two adjacent vertices receive the same color. And the minimum number of colors required is the chromatic number. And Brooks theorem says that this chi g is bounded above by delta g or delta g plus 1. If it is a complete graph or odd cycle, this is the case. And in this case, we can also have an algorithm like greedy algorithm will give you this bound also. Edge coloring, similarly, you elements here are the edges. And two edges are adjacent, then they should receive the different colors. So this is called the chromatic index, or the edge chromatic number or chromatic index of the graph, the minimum number of colors. And Weijing's theorem says that this can take only delta d or delta g plus 1. But deciding this thing is a hard problem. And when for a class of graphs, for a graph, this is delta g, then you call it a class 1 graph. And this is called class 2 graphs. So this is classification of this also is an important open problem. A lot of work is going on. So this whole process is basically a matching. So, and to get a matching, possibly if you have a high degree graphs, then you look for a Hamilton cycle and alternative edges will give you. So this cycle decomposition, factorizations, matching, all those things comes into this, the edge coloring. This is a very rich area. Total coloring, it combines both the things plus something extra. So first of all, the elements are vertices and edges that has to be colored. No two adjacent vertices should receive the same color. No two adjacent edges should receive the same color. And a vertex is incident on the edge, then the edge and the vertex should also receive different colors. So, so in fact, if you construct the total graph, that means the elements are vertices and edges. And whenever two vertices are adjacent, so in the total graph, they will be adjacent. Whenever the edges are adjacent, they will be adjacent. And the incidence also will be captured through it. So it is basically the chromatic number of the total graph. This total chromatic number. And this is denoted as chi tg or chi double dash g. So there is a long-standing open problem or conjecture saying that in the case of edge chromatic number or chromatic index, that is between two numbers delta g and delta g plus 1. Here it is delta g plus 1 and delta g plus 2. That is the conjecture. So this one is easy because this is trivial because you have got delta g plus 1 elements, delta g edges and the vertex. They should receive the distinct colors. So this thing, but the other one is conjectured to be true. And in fact, there is strong evidence that this conjecture will be true because the if you see probabilistic approach, or that almost every graph is basically satisfy the TCC. So this is the conjecture. And suppose for a class of graphs, this result holds, then you can talk about type 1 graphs and type 2 graphs. So where it will take delta g plus 1, then it is type 1, else it is type 2 graphs. So this is a classification, and now proving this conjectures to be true for certain classes of graphs are the current area of research. And of course, look for bounds and other kind of things. So in this talk, we'll talk about only one class of graphs called complete multipartite graphs. So you have got P parts. So V1, V2, P are independent sets, and between any two parts, between any two vertices in these different parts, there is an edge. So this is denoted as K, R1, R2, Rp also. This is the cardinality of the number of vertices. Yeah, Vi. This is the partition basically. So for example, this is K2, 3, 3. That means two elements, 2, 3, and 3 elements. And between this is a complete bipartite graph, right? All possible edges are there. So this is, though, very nice structure, but this is still it has sufficient complexity. For example, for many parameters now are still open for this particular class of graphs. And if you see the chromatic index, so this Brooks theorem came much earlier, but in only 1992, this classification for class 1, class 2 graphs with respect to chromatic index was settled. And it was by Hoffman and Rogers. They said that this is class 2, this is class 2, that is chi dash g is equal to delta g plus 1, if and only if it is overfull. Overfull is the number of edges is more than delta g into n by 2 edges. And this is a very easy necessary condition, because these many edges you cannot pack into this delta g parts. So it needs to be this, but this is also sufficient. This was shown. It's a very classic paper. So in the case of this complete multivariate graph, also this problem is still open till date, and there are certain conjectures. And remember that this classification, for example, for regular bipartite graph, this problem is NP complete to decide whether it is class 1 or class 2. But it is a complete multivariate graph, and it was solved. And this is also similar to this. For example, this total coloring problem or chromatic total coloring number for complete multivariate graph. For regular bipartite graph, deciding whether it's type 1 or type 2 is still NP complete. But the way this problem was resolved for chromatic index, people feel that this can be solved. Basically, we can classify. So, so this, first of all, whether it satisfies the TCC, total coloring conjecture, that is first problem. So this 1971, that is 56, that conjecture was there. 1701, it was shown that for balanced complete multivariate graphs, this conjecture holds. That is, all parts are of equal size. So after 71, in 86, now these people, Chetwin, Hilton, Yap, Wang, Zhang, these are big groups. They came up with a nice technique. Maybe tomorrow I'll elaborate on this. So they said that if you have a sufficiently large independent set, that means G minus S is less than or equal to delta plus 1. If that is the case, then in this total chromatic number of this will be less than or equal to delta plus 2. So if this is the case, if a large independent set satisfying this thing, then it will satisfy the TCC. So for a complete multivariate graph, this in fact large independent sets are there. For example, if you take a complete multivariate graph, you take the largest, this is arranged in the increasing order of their cardinalities. So you take the last set, VP, that is a large independent set, and now this minus VK minus S is less than or equal to delta G plus 1. So for this particular class, total coloring conjecture holds, and this was done in 89. So this is 71, and then 86 the result came, and then finally it was done, 89. So we know that the TCC holds for complete multivariate graph. So the next thing is to classify for this coloring, for total coloring, odd in the cardinality odd, or the order is odd. That means odd number of vertices are there. It is slightly easier to handle. For example, see, if you take a color class in total coloring, so some vertices and some edges should be in the same color class. So the odd, then you can take one and then you look for a matching, right? A remaining graph, you look for perfect matching. But it is even, then how to color the vertices, that becomes a problem. So, and this is reflected in this result also, that in 92, it was shown that for complete multivariate graph, where the number of vertices is odd, then this is class 1, and it was resolved, classification. But even cases, this is still open. So, and of course, another result came for balanced complete multivariate graph, the conjecture holds, and this classification also is done in 74. So when all parts are same. So this is a regular multivariate graph. So regularity, the graph is far away from regular graph, then this becomes a problem. And that is captured through a notion called deficiency in a graph. So deficiency is basically degree delta minus degree of a vertex summation over all v. So that is a measure which shows that how far this graph is from the regular graph. So this Hoppen and Roger now came up with a result saying that it is even order now we are discussing now because odd is complete now. So even order graph, deficiency of this graph is greater than or equal to 2n. 2n is the number of vertices now, minus r1, the first part size. If p is equal to 2 parts, or p is even and r1 is odd and r1 is equal to rp minus 1. If this is the case, and these are arranged in the increasing order, r1 is equal to rp minus 1 means all these things except the last are all sames. R1 is equal to R2 is equal to RP minus 1, all sames. And otherwise, the deficiency is greater than or equal to 2n minus RP, the last part, then K is of type 1, where deficiency of G is, this is the degree of this is the difference between the maximum degree minus degree of that vertex. That is the deficiency of that particular vertex. You sum over all the vertices, that is basically deficiency of this. This is the little bit far away. Deficiency is more. For a regular graph, deficiency is equal to 0. So this is the result, and there is a conjecture saying that complete multi-edge graph is of type 2 if and only p is equal to 2. That is well known. 2 parts are there, like bipartite graphs. K is bipartite, complete bipartite graphs, and K is regular, or VK is even, and deficiency of K is less than the number of odd parts of odd sizes. So deficiency, this number of parts of odd sizes, because we are the V is basically even size, and if we count the number of parts which are odd in size, and deficiency is less than that, then it will be type 2. Deficiency is greater than that, that will be type 1. This is the conjecture. So, so there are, see the chronological order, the years in which these are given. So the first result came in 92 by Chiu and Yap. They say that this R1 is less than R2. The first part size is less than equal to, strictly less than second part. Then this is type 1 graph. And this result was after 8 years, it took to extend this result, that if R2 is less than equal to R3 minus 2, then this is type 1. And of course, this is even graph. This is for any graph, right? Then we improve this result. It is R2 is less than equal to R3 minus 1, but R2 is less than R3. R2 is strictly less than R3 in this. So this is basically, this is Chris Rogers. He visited basically India for some conference, and then I hosted him. And prior to that, and we initiated the work, and finally, he is a person who has worked extensively in this area. So this is the improvement, and this used some different technique. Earlier, all the techniques are some other traditional techniques. Here, there is a change in the technique, and using that, it was shown. And then recently, we have done that it is extended for the next part. That is R3 is strictly less than R4. Then also it is type 1. So this is basically the number of parts. So the result is up to this point. So beyond other things, nothing is known. And result based on the number of parts. How many parts are there? 3 parts are there. 3-partite graphs of even order. Then K is of type 1. 4 parts in 2000 it was done. If that particular conjecture which is given is also valid for this, if and only deficiency of K is less than the number of parts of odd size. So for 4 parts is done. 5 parts, Dalal and Rogers, they did it. For 5 parts, also that conjecture which is given, the deficiency of K is less than the number of odd parts, the number of odd size parts. So this is basically 2. Up to 5 part it was there. And the technique, earlier traditional technique, this is one called beta biased coloring. And there is another technique which was introduced by, in fact, adopted by Rogers and Dalal for this particular problem called amalgamation technique. So the beta bias coloring is basically you color the vertices of one part. Basically, you are looking for a total coloring. So some vertices will require a particular color. And for remaining set of vertices, you have to look for edges that you have to give. That means you look for matchings. So color the vertices of one part using one color. Then color the maximum matching M in the remaining graph G minus beta with the same color. So look for a maximum matching. Looking for existence of big matching, you require different kind of technique. Like you require the graph to be high degree graph. Then you can use Dirac's kind of theorem to find out a large cycle. Or you look for, very recently, that was the technique basically. Almost all results were based on Hamiltonian cycle or large cycle. But very recently, the Todd's theorem is used now to look for a perfect matching or near perfect matching. There is a very recent development. So you somehow find a maximum matching, or you can look for maximal matching also and color it with the same color of with the beta. Once you do it, then add a new vertex, and this is dummy vertex to the graph except for the vertices in beta. And you take a new vertex and V minus beta you join to every vertex. Using the edge coloring technique, find proper edge coloring of the graph. G star is equal to G plus V minus M using delta G star color. So this can be delta of G star. So basically it can be either sum of delta. So this kind of results, there is an interesting result saying that if for a particular graph, the maximum degree vertices, these are called major vertices. The major vertices induces a forest, then it will be of class 1. This is a very classic important result. So most of the cases you get this kind of result, but sometimes it doesn't work. For example, this complete multiplied graphs K R R R R R R 1 2 3 4 5 6 7 parts. Now if you take this thing, the core of the graph, many high degree vertices are there. So if you remove one part, still this graph, the core of the graph is this subgraph induced by the maximum degree vertices is not a forest. So this possibly, if you take one more color, then you will exceed this delta plus 2 colors. So that will be a problematic thing. So if delta color, because then one color you have used, so you can look for delta plus 1 color. Otherwise, delta plus 2 colors, anyhow it can be done if the TCC holds. So that is a problem. So there is a limitation. So, and this technique was basically graph amalgamation technique, which is very extensively used in the graph edge coloring problem. And of course, the total coloring, most of the time, the techniques are borrowed from edge coloring and extended to this total coloring. So this is basically in the light of, you can apply to any graph, but basically this is, we are talking about multipartite graph. So these are merged into a single vertex, or basically mathematically. So amalgamation is a like pair of functions from vertex set to vertex set of G to vertex set of H. So this is a homomorphism kind of thing. For example, several vertices, the vertices of here goes to more than one vertex may go to same vertex. So these vertices has gone to this has gone to this and this. And the side S is a function from edge of G to edge of H. So that E joins U and V. Then if and only phi dash E joins psi of U and psi of V. So these two properties are there. It is something like, if you pictorially, you take a subset of vertices and then collapse into a single vertex. And if in between there are edges, then you put self loops. So this resulting graph is a multigraph. So graph coloring classically is studied for multigraphs. So for example, the Weising's theorem also was initially for multigraph, and for For graph, this was a corollary, that what you see. So you get into a multigraphs. So you multigraphs, you do the coloring, and if you from this, you come back to this. This is the problem. So there is a result. So associated with this psi, associated with this amalgamation, there is a number function. So for example, here three vertices have gone to this one. So from here I can define a number function. So phi of 2 is equal to 3, phi of 1 is equal to 2, phi of 3 is equal to phi of 3 is equal to 3. That means this psi inverse of 2 cardinality of that set. So n of v is equal to psi inverse v cardinality of that. That means you keep track of how many vertices are merged together to a single vertex for each vertex in the second graph, right? And okay. Okay, so now G is a detachment of H. If there exists an amalgamation function psi of G onto H, so that psi inverse V, this cardinality is equal to NV. That means from the graph G, you have gone to H. From H, you want to do the detachment. So G will be a detachment, so that amalgamation of G is equal to H. So now the subgraph of G induced by the edges colored J is denoted by Gj. And for a graph, this Mg of UV denotes the number of edges joining vertices U and V, because we are now talking about multigraphs. And IgV denotes the number of loops, basically, incident on U. That means two vertices which are adjacent in G goes to a single vertex X, then there will be a loop in the amalgamated graphs. Now we'll use these notations. This X and Y are approximately same if one lies in this thing. So that means this should be somewhere Y should be there, right? Okay. So X is related to Y means approximately same means this is X lies between the floor and ceiling, or Y lies in the floor of X and ceiling of X. So almost integer wise, they are very nearby. So now this is one of the important theorem which has wide applicability in the coloring. This is Bahamian and Rogers theorem. Let H be a KH colored graphs and N be a function from VH to N. So that means you are in a multigraph, and using K colors, you have colored the edges of the multigraph, and N is that number functions. So how many vertices of G have been mapped to each vertices, that is captured by N, so that for W belongs to VH, NW is equal to 1. That means only one vertex, NW is equal to one vertex has come, then there is no loop. IH is equal to 0. There is no loop in the multigraph. Then there exists a loopless N detachment G of H with amalgamation function psi from VG to VH, N being the number function associated with psi, such that G satisfies the following conditions. Now you can possibly get from H to G, but a colored graph, you are coloring a multigraph and you want to come back to G and make it a proper H coloring. So this theorem gives you the guarantee that under certain conditions it is possible to do that. What is the conditions? Satisfy the following condition. Degree of U in G is approximately same as degree of W in H divided by N of W. So how many vertices are there? Suppose 5 vertices have gone to W and degree of W is equal to 25. Then degree of U should have been 5. That is 5, 5, 5. So those vertices have gone to this. There is no loops. So this independent set has gone to this. So equitably now we can come back to the graph G. And for U belongs to psi inverse W. This is the case. And now if you have the colored the degree of GJU is approximately same thing as the degree of HJ. HJ is the color class. H is now colored with K colors. take a particular color J, the set of edges of color J which will induce the graph is called Sj, that is color class Sj. And in that graph, you take the degree of this and divide by n of W. That should be a degree of this thing in the graph G, original graph. So that means from edge coloring, suppose between two vertices in H, you have got 5 edges of same color. Now, if n of W, for if you will, for example, nW is equal to 5, then equitably you can come back and distributed those colored edges to H. So now you want to do the edge coloring of G, then if you can do the amalgamation and go into H, which is a multigraph, and multigraph, it may be easy to color. Once you color this, right, you can come back to the original graph satisfying these two conditions. So more or less, you will be able to manage the edge coloring. And then because you are looking for total coloring, in fact, it was used for edge coloring, but you want to use for total coloring, those edges, vertices are also there. You need to take care of that. So with those same colors set, you should be able to do it. And these two conditions are for multigraphs. So at present, because this edge coloring is classically for multigraphs, so third and fourth conditions, for example, how many multiple edges are there between two vertices, this also equitably that will take care of that. So for our discussions, only these two conditions will suffice. Okay. So what you do is that let K dash be the amalgamation of the complete multiply graph K, where V of K dash equal to K dash, psi and n be the amalgamation function and the associated number functions. So V of K dash, we will take the, here V of K dash equal to n of K dash means 1, 2, 3 up to K dash, and the natural number will take. So the second thing is that find delta K plus 1 subgraph of K dash, each with degree sequence measured by n of 1 to n of. Very important step, because you want to color each subgraph is basically one coloring. So you want delta K plus 1 coloring of the amalgamated graphs. And now you want to come back to the original graph. But if you use too many edges with the same color, then you will not be able to come back and color, have a proper edge coloring. So this color class will induce a graph whose degree sequence must be measured by its number function n of 1, n of. Okay. So if you can do this particular thing, so this is the crucial step. If you do this thing, then if this condition is satisfied, then you can use this Bahmanian-Rogers theorem, and that will take care to disentangle. That means you can come back. That will guarantee those two conditions that you have said. Right? It will guarantee these two conditions. If this is the case, then you can come back to the original graph and have a edge coloring. So this is this particular step is a quite involved step, and it is basically graph specific. If you do well, you will be able to compete, otherwise not. Okay. So basically, our technique follows the 4 general steps. Okay, many color classes of K dash with degree sequence n of 1, n of K dash, saturating all the vertices are found. The remaining edges of K dash are partitioned into few remaining color classes. Using the Bahmanian-Rogers theorem, K dash is disentangled to K. Most vertices of K are then colored using colors in step 1. With some color class, some color is missing, then we can give this particular color in step 1. Left one are colored using colors in step 3. Remaining edges, when you color it, some colors are missing, then those colors can be given to the non-incident edges. And similar technique was used by this Dollar and Rogers. But the important point, I just will say, so the earlier, this previous result, 2014, what they did that all complete part, each part has gone to a single vertex. So, but if you do this particular thing, okay, so this Dalal and Rogers they did, that is 5 parts, each part has gone to a single vertex. So this Amalgamated graph is only K5 multi graphs. K5 means 5 vertices are there. But if you do something, let me see first of all. Okay, for example, this particular case, I'll come back to the previous slides. Now, suppose if you take, this is the sixth part that we are talking about. If you apply the Dollar and Rogers result, which requires coloring of all vertices in the same part, in the same color, and if you take all the vertices in same part in one color, then it will, this method will take delta G plus 2 colors. So our aim is to do it delta G plus 1 color, that will be defeated. So earlier technique cannot be extended, so you have to do something different. And for that, what we did is that we, instead of all the parts, each part, all the vertices in one part will go to single vertices. Now some part will go to different vertices. In other words, you, some vertices in one part may get different colors. So till date, all the vertices in one part you are getting the same color, but that part is now, if you do it, you will not be able to do. One example we have. So that is basically the change. Okay. So now when you look for complete 6-parted graphs, so using this earlier results, like for example, R1 is less than equal to R2, then it is delta, type 1. R2 is less than R3, delta 1. R3 is R4. This particular theorem will tell you that is class 1. So looking into this all possibilities, now only these 5 cases are there. You need to handle. Just 1 minute, maybe I'll complete. 2 minutes maybe. Okay. So and then, for example, is R plus 2 and R plus 4. If you take the moment you take, because we are talking about the even number of vertices, R and R plus 6, if you take, now the deficiency theorem, that is deficiency of G is greater than or equal to 2n minus the first part, last part. If that is the case, then automatically it will be type 1. So that will take care of that. So only these 5 cases are there. And out of this, most difficult case is this one, when this is all parts are, 5 parts are R and then R plus 4, when R is odd. Because these cases, the earlier technique cannot be utilized. So instead of 6 parts, you have to amalgamated graphs, you have to have more than 6 parts. So we did for 7 parts. And yeah, so what you did is the following. So the psi of Vi equal to 1 for first 5 parts, it is single vertex. For 6th part, you take one vertex and make it to the 7th part, and remaining vertices you put in the 6th part. So we have got 7 vertices instead of 6. The associated numbers are, for this thing is R for 5 parts, 6th part it is R plus 1, and 7th vertex is 1. And now you require a lot of other things. For example, this is a multigraph. What is this multigraph? 6 copy for vertex 1 to 6. That is R minus 1 copies of K6 are there. That is K6, each edge is separate how many times? R minus 1 times, plus 4 times this complete bipartite graph. 1, 2, 3, 4, 5 is one part, 6 part is there. So 6 to all these 5 vertices will be there, 5 edges will be there, and multiplicity will be 4, plus this complete bipartite graph. And so, and such that the degree sequence of each color class is equal to this. So we have proved this thing that for this multipartite graph, there is a equitable 5-edge coloring. So what is equitable 5-edge coloring? So you have the edges incident on a particular vertex. So the number of edges of 2 different colors incident on a vertex, they differ by at most 1. So it cannot be the 5 vertices, 5 edges are same color. Then you will not be able to disentangle. You cannot now go back. So it will be equitable coloring if this exists, and there is a decomposition. So that can be decomposed into 6 cycles of length 5 with vertex I missing. And this existence will come from some result called Brand's result. This is a decomposition result. So this is what we are going to do. These are the 6 color classes. Then you take a matching, 5 matching, and then which will induce this particular graph. And then take R minus 1 copies of these matchings. This is a color class. Then C1, C2 with the decomposition of K5 into 5 cycles, these 2. And these are basically C5R plus 5. So these are the basically different color classes. So that means they will take one colors in the amalgamated graphs, and each one, when you go back, we can spread properly, which will give you a delta plus one color. So then we apply. So this result will, once you have this partition, now this Bahmanian-Rogers theorem will guarantee that you can go back to the graph H and properly do it. So this is one example which is given for R is equal to 3. So this is equal to W1. This is a cycle of length 5 by not including the vertex 1 plus this. So this plus this. So this will be one color class. This will be another class. So you have to define all 20 color classes, and these color classes for R is equal to 3 basically. So these color classes, once you define, you apply the theorem and go back to the proper total coloring of the graph. So K is equal to 6. Now it is resolved. In fact, one of the referee had asked, so can this technique be applied to other parts, like 7 parts and other things? So notionally it will be possible, but getting these color classes and other things will be very, very tedious. So we checked for some cases, it was done, several cases anyhow will come. This will be case analysis, and so some more technique needs to be developed before attacking the general program. But so up to 6 parts, and R3 less than equal to R4. Basically, then it will be the case. So that means R1 is equal to R2 is equal to R3 is equal to R4. That will guarantee. After that, the work is still left, and now it has taken maybe several 30, more than 50, 40 years to resolve this problem. Though, and maybe tomorrow's lecture we'll see there is a strong evidence that all these conjectures like TCC seems to be true. With this, I'll conclude maybe, and then you can read. I think detail is given in the paper. All the decomposition for all the cases, and how to do it. That is the main important part. Then only you can do the coloring. Okay. Sorry for taking someone extra. Only overview have understood, then one can sit down and then work it out. That request. Okay, before you go, you give me a gift first of all, Sandeep. Before he leaves, he has to give me a gift. Or to him.
Hi all. First of all, let me welcome you all to my presentation for CALDAM 2024. Myself, Sri Lakshmi Sugumaran. I'm a third year research scholar from Central University of Tamil Nadu. I'm doing my research under Dr. T. Kavaskar in graph theory. My guide itself is the co-author of today's paper that I'm going to discuss here. So today, I'm going to discuss with vertex coloring, and if we are giving colors to the edges of a graph only, then such coloring is said to be an edge coloring. Here we are coloring, giving color to the edges only. So one here, two, three. Again, I can do here like that. And there is a condition for coloring that I will explain you. Then in our paper, we are dealing with the total coloring, which is we assigning colors to both the vertices and edges. So I'll take this same figure, this one. Vertices as well as the edges distinct colors such that
Hello. Hello.
colored using 1K. So this should be colored using some tool, and this one should be some three. So again, two cannot be given to any of the edges that are adjacent. Within this vertex, and we cannot be given to any of the edges or vertices that are adjacent this edge. So I can give one here. Uh, so I will give some four here. Some new color. Again I can give one here. So this one I can give three here. I can give four here. So this is a proper total coloring of this particular graph. So total coloring means assigning colors to both the vertices as well as the edges, and it should be in such a manner that no two adjacent or incident components are receiving the same color. This is the outline of my presentation. First of all, we will discuss some preliminary definition that are needed the uh, for understanding the proofs that I am explaining here. Then PCC is the topic that we are discussing. We are going to prove PCC or verify PCC for a particular class of graphs. PCC means total coloring conjecture. And I will explain the conjecture and also some non-results conjecture. The new results, that is the results that we have found in our research and various sciences. So the preliminary definition, total coloring, I have explained already. Then K total coloring, if we are using K colors, then it is a K total coloring. This is a four total coloring. We are using we are giving total coloring to this graph. I will name it as G using four colors. So this is a four total coloring, and the least number of colors needed for the proper total coloring of G is known as the total chromatic number of G, and it is notated as chi of G. Similarly, for a vertex coloring, the least number of coloring that are needed for a proper vertex coloring is known as the chromatic number of G. Chromatic number, and it is notated as chi of G. And for edge Coloring also there is a least color. Is the chromatic index of G, and it is notated as chi dash of G. We will be seeing these notations in our proofs, and this is chi T of G. Total chromatic number. Some examples are vertex coloring. Actually, there are two uncolored vertices here. So from the figure we can see that both of them can be colored using because they are not adjacent vertices, and there exists no vertices adjacent to these uncolored vertices that having color. So two can be given to both of these vertices. Now the second figure it is an edge coloring using two colors, and the third figure is a total coloring using five colors. Now the conjecture. That is total coloring conjecture. So in 1960s, that is before more than 60 years before, Belzer and Weissing, they independently raised the following conjecture. So regarding total coloring, we can observe one thing. So let G be a graph having maximum degree delta of G. So we can find a vertex say V having its degree delta of G. So for delta of G, edges are incident with this particular vertex. If I give color 1 to this vertex, then I can't give any of this delta distinctly. So I can give three edges for this edge, and particularly we have delta of G. So the last edge should be given the color delta of G. So for any graph of delta.
Hello. 1, 2, 3, 4. Hello.
Can I take my slides on?